Welcome to AI Frontiers. This podcast episode dives into the world of computational engineering, exploring recent advances in research as reflected in papers available on the arXiv preprint server. Computational engineering, categorized as cs.CE on the arXiv preprint server, is a multidisciplinary field. It leverages computational methods to solve complex engineering problems. This involves using computers, algorithms, and numerical techniques to model, simulate, and analyze systems and processes across various engineering disciplines. These disciplines include mechanical, civil, chemical, and electrical engineering. The significance of computational engineering lies in its ability to handle problems too complex, expensive, or dangerous for traditional methods. It allows engineers to explore designs, optimize performance, and predict behavior, leading to efficient, reliable, and innovative solutions. A key research theme is optimization and control. This focuses on optimizing system performance and developing control strategies. Such strategies often involve complex environmental or economic factors. For example, Liu et al. In 2025 addressed submarine search and rescue optimization under environmental uncertainty. Kim et al. In 2025 tackled thermal comfort control using reconstructed environmental data. A central goal is achieving peak efficiency under real-world constraints, balancing performance and cost considerations. Another major research theme is data-driven modeling. This approach uses machine learning, especially deep learning, to create predictive models from data. Schuthoff et al.'s 2025 work predicted field permeability in oil reservoirs. Scott et al. In 2025 focused on forecasting solar power output. These studies demonstrate the power of large datasets to create accurate predictive models for a wide range of engineering domains. Metamaterials design forms another important research theme. Several papers explore the design and characterization of metamaterials. These are artificially engineered materials with properties not found in nature. Studies often involve computationally intensive simulations and surrogate modeling techniques. For example, Danesh et al. In 2025 investigated structure property linkages for stochastic metamaterials. Rosenkrantz et al. In 2025 worked on data-efficient inverse design. Surrogate modeling involves the creation of simplified, computationally cheaper models. These models approximate the behavior of more complex simulations. Techniques like Gaussian process regression and neural networks are used. Surrogate models are particularly useful for optimization and design space exploration. This results in speed and efficiency improvements over full simulations. Algorithm selection and optimization is a crucial theme. Efficiently selecting the right algorithm for a specific computational task is increasingly important. Newcomb et al. In 2025 specifically addressed algorithm selection in molecular dynamics. Balancing accuracy and speed, and using adaptive strategies, can greatly impact simulation performance. Several papers presented noteworthy findings. Liggegard et al. In 2025 demonstrated that wavelet compression reduces smart grid costs. Rosenkrantz et al. In 2025 showed that neural networks reduce the data needed for metamaterial design. Kim et al. In 2025 highlighted spatially reconstructed temperature fields enhancing thermal comfort. Newcomb et al. In 2025 found algorithm selection speeds up molecular dynamics. Wu et al. In 2025 presented reputation and data privacy preservation for mobile crowd sensing. Fangnan et al. In 2025 showed deep reinforcement learning algorithms can be used for Bitcoin and Ripple cryptocurrencies trading. The papers showcased a variety of methodologies. Finite element and finite volume methods are used for simulating physical phenomena. Machine learning is applied for image processing, forecasting, and surrogate modeling. Monte Carlo methods are used for simulating systems with uncertainty. Decomposition techniques are used for time series analysis. A seminal paper is Kim et al.'s 2025 work, titled Evaluation of Thermal Control based on Spatial Thermal Comfort with Reconstructed Environmental Data. The objective was to improve thermal comfort with spatial data. The method involved using GAPI-POD, or proper orthogonal decomposition, for temperature field reconstruction. The findings showed reduced error in temperature estimation. The significance lies in improved energy efficiency and personalized comfort through spatial data reconstruction using sparse sensors. Another seminal paper is Danesh et al.'s 2025 work, entitled Reduced Order Structure Property Linkages for Stochastic Metamaterials. The objective was to efficiently link the design space to mechanical properties. The method used principal component analysis, or PCA, fast Fourier transforms, or FFT, and Gaussian process regression, or GPR. The findings showed a reduced dataset size while maintaining accuracy. This accelerates metamaterials discovery by combining dimensionality reduction and fast simulation. The paper by Likegaard et al. In 2025, titled Data Compression for Time Series Modeling, a case study of smart grid demand forecasting, addresses the challenge of reducing data volume without sacrificing forecasting accuracy. The method used wavelet-based data compression. The findings indicated XGBoost, or extreme gradient boosting, is robust to compression artifacts. This approach enables scalable and efficient data management, especially for renewable energy systems. Future directions in computational engineering include the integration of machine learning with physics-based modeling. Developing data-efficient algorithms is crucial. Addressing the black box nature of AI models and robust uncertainty quantification methods are also important. The overall goal is to empower engineers to design more sustainable systems. This presentation was synthesized using Google's GPT models, specifically models/Gemini 2.0 Flash. The text-to-speech was synthesized using Amazon's TTS services. Image generation was achieved using Google's image creation models. The synthesis has been reviewed by human experts. However, potential oversights may exist. All references are provided. Subscribe to AI Frontiers for more insights. The podcast is titled AI Frontiers and provides coverage of AI developments.